So we learned the formula and the general multiplication rule follows directly from the formula. Now let's think about a different probability. What is the probability of not having high cholesterol given smoking? Try this again. 3, 2, 1. The answer is simple. Again, delete this column and compare like among these probabilities, we are interested in this guy. So 9.43% out of the total of these two probabilities. Then you get 19%, approximately 20%. And remember that. So the reason why I have you calculate this is because I will compare probability of not having high cholesterol among the smoking, and compare that to probability of high cholesterol among those who smoked. It is 19 something, it is 80 something. So they sum to 100% by construction because their denominator both have the same condition, so they have the same denominator. The denominator is determined by the condition, so they have the same denominator, and the sum of their numerators are exactly the denominator. Because, think about this. Among those who smoked before, they have only two choices. Either they have high cholesterol or not. So if they have high cholesterol, they will count toward this probability. If not, they will count toward this probability. So anyhow, they're going to be counted, so the sum must be 100%. Everyone who smoked before will be included in either of the two probabilities. So this is the complement rule for conditional probability, right? So two events, so complements exhausts the whole probability. And what you have to be careful here is you have to have the same condition. Condition must be the same. Sometimes people mistake, like they tend to put complement here on the condition, but that's not. You maintain the same condition, but take the complement of the main event of interest. So this is the complement rule for conditional probability. Idea is the same, simple. Given the same condition, it's either yes or no. So should be 100%. Okay, let me go to another example and a more light example. So now we are going to consider another question. Suppose you are, say, you are choosing like whether to go to, suppose that you are interested in a graduate program and you have two options. One school has high tuition, you have to pay high tuition, and another, there is the other, you get another offer from a low tuition school. Then you are considering whether it is worth to pay high tuition or not. So what we would like to study here is we would like to learn, examine the relationship between high tuition and high salary. If you graduate from a high tuition school, would you will you be more likely to earn higher salary or not? So I will denote high tuition school as T and graduation from high tuition school T and high salary as S, right? So you would like to study this. And then again, which probabilities do you need to compare? Think about this. Think more carefully, and if you are not sure about the definition, go back slides and see what happened. I will turn the page The answer is these two. You are comparing the probability of high salary if you graduated from a high tuition school or if you graduated from a low tuition school, like not a high tuition school. So you are changing the condition and comparing the same probability, right? And suppose this is the data. This is the data made of numbers. Of course, there is no such data, and there is no definition of clear definition of high tuition. Just conceptual example. Then you calculate those two probabilities and compare. Do it by yourself. So you have to do all the job by yourself, how you calculate the conditional probability and how to compare them. It may take time, but you gotta do it. Pause the video and I will show you the answer. See if your answer is correct. So if you calculate high salary given high tuition, you erase the second row and calculate the probability from the first row only. And the other condition, T complement, is from the second row and high salary. And they are the same. They happen to be the same, and which means that high tuition does not increase the chance of high salary according to the data, this uh, fake data. Okay, so it's interesting. So interesting, not the main, not the example, but the same probability. This is a special statistical phenomenon. So we are going to study what's going on, uh, what's other properties we can see in this case. So calculate the probability of simply high salary. So ignore tuition and calculate high salary. Then you have to sum all the outcomes, which is simply 100%, of course. Out of 100%, these two types of outcomes satisfy high salary. So the sum of them is 25%. So only two outcomes satisfy high salary. So you can calculate the probability as 25%. So then you can see that these three probabilities are the same. Probability of high salary is always 25% unconditionally, no matter what your tuition is, or if you graduated from a high tuition school, if not. So in any case, it's always 25%. So that's what we are interested in. It's an interesting uh, thing, and we call this statistical independence. We say two events are statistically independent if these probabilities are same. So probability of A happening equals probability of A happening when B already happened, which always also equals the probability of A happening even if B did not occur. So regardless of B, so B is unknown or happened or not, probability of A is the same. You may change the role, like switch the role of A and B. Probability of B is the same no matter what happened to A, right? Even if it's unknown or happened or not, still the same. So this is the definition of statistical independence. So two events do not affect each other; they are the same, no matter what the other guy are doing. Interpretation. There are many interpretations connected to this notion. So you may say that the event B is not effective to change A. So you'd like to like increase salary by paying more tuition. That's not effective. Or information B does not help predict A. So you'd like to predict your salary based on your tuition, but you cannot. It does not help. Tuition does not help predicting your predict your salary. And between different groups of B, the outcome is the same exactly. Different tuition groups, the salary, high salary probability is the same. And also in economics, similar structures, the similar statements can be found, like today's stock return is independent of tomorrow's or not. If it's independent, then you cannot predict the future. If independent, but if they are not, then there is some room for like a additional return, like by predicting the future. Or let's think about this: Chinese GDP independent of the US. It's interesting if they are independent, and then you don't need to care like so. Then you cannot predict one using the other, or like say what happens in China does not affect the US, but usually they are not independent. So what's independent within the economy is an important question to understand and to better predict the economy. So, and then another interesting result from based on the statistical independence is the special multiplication rule. It is called special because the general rule is written this way. General rule writes the probability of intersection as a conditional probability times a simple probability. But the conditional probability is not clean. So if you additionally assume that two events are statistically independent, then the probability of intersection is a simple multiplication of two probabilities because these are the same. This is the general rule. It holds in any case all the time, but this is true only when they are the same. So they are the same if they are statistically independent. By the way, so you may find a similar structure in here with the special and general addition rule that we learned in chapter 1. Yes, they are similar, but they are not related to each other. They are totally have nothing to do with each other. So even if two events are statistically independent, it doesn't mean they are mutually exclusive or vice versa. So there is no, just the structures happen to be the same, and statisticians made up theory to make them parallel, but there is no relationship across them. Okay, so in the next video, I will show you how to test whether two events are statistically independent or not. It's interesting and important. So see you in the next video.